I'm Emily Michelle Olmsted, and I'm here at the Massachusetts Alternative Septic System Test Center, or MASTC, joined by George Hoyfelter, the former director. And we're here to talk about wastewater and innovative alternative septic systems, and specifically troubleshooting them for common issues that may occur. George, where do we begin?
Well, I think first a short explanation of what an alternative septic system is and when they're used. Alternative septic systems are generally used to overcome shortcomings in the ability to put a standard system in, or to actually get better treatment in areas where it's needed, such as on Cape Cod. The big one is nitrogen. You might want to remove phosphorus, or you might be so close to a resource that would have implication for pathogen transport, you might want to disinfect. So there's all different types of alternatives. Beyond that, there are the leaching components that are considered alternative, but today we're focused really on those components that are mechanical.
Okay, and you say close to a resource, you're referring to groundwater?
Groundwater, or a shellfish resource or swimming resource or well. Okay. All of those are tied into groundwater in Cape Cod.
With innovative alternative septic systems, you have inspections and you have samples. What's the difference?
Well, a sample is pretty simple. You're going out there to sample, and you might do that before you go out to inspect, because when you inspect, you're also probably sort of looking for adjustments you might have to make, and the sampling would inform that adjustment that you would make. So sampling, you're just going out, grabbing a sample, taking it to a certified lab or doing some field sampling. And then with inspection, you're really looking at all the major components, making sure they're functioning properly. And in some instances, you're making sure the owner hasn't unplugged it, and that all those components are functioning as they should in concert with one another to achieve your treatment.
And with samples, we have effluent and we have influent. What's the difference between those?
Well, the effluent is the sample before it goes into the leach field. In most cases, it's right before it is released to the environment, where the influent is what is exactly coming out of the house, which is probably one of the tougher things to sample. And in some alternative septic systems, you can't sample it adequately because there's a mixing that occurs within the unit process that prohibits you getting a clean influent sample, if there is such a thing.
So if I'm understanding you correctly, to get true influent is difficult for most of the existing IA systems, or depending on the situation, just because of how much influent and effluent are usually mixed? Is that
mixed and reprocessed, because a lot of the treatment is really running it through the process treatment a number of times before it is released to the environment. So it mixes it with the incoming wastewater, sometimes to get a carbon source for denitrification, for instance, and sometimes just to re-aerate it and retreat it and knock the BOD, or biochemical oxygen demand, down.
And there are quite a few different IA technologies on the market today and in place on Cape Cod, and they're all a little different.
Oh yes, there are different treatment processes, some which are fixed activated sludge, which is really just sort of a mixed liquor, mixes the influent with aerated effluent and achieves denitrification one way. There are others that are trickling filters, which use a media to take the influent, trickle it over a media, and then recirculate some of that, or sometimes just a single pass and then go forward, depending on sort of the target contaminant you're trying to get rid of.
And so the troubleshooting we're talking about are general patterns to look for that don't depend on the IA technology?
Correct. We'll look at what we do when we don't achieve the final result. What you have to do in between to adjust that could be varied depending on the technology, but the signals for what you need to do, where you need to do it, will be given by pretty much the sampling you do.
So where do we begin as far as starting the process?
Well, to do good maintenance, you need a good sample. You need the good information. You need to find out what's going on. So it really begins on the designer's table. The designer has to put a good sampling port in that gets a good representative sample and doesn't skew the results so that you're not operating blind. So these are things like a distribution box before the leach field. They should be designed such that they're easy to get at and easy to get a free flow sample. I've seen instances where they design the D-box and somebody dips down into the D-box or pumps out of the D-box and gets sludgy stuff that's been settling there. And then they're going to come to a different conclusion about how that system is operating compared to if they got a good free-flowing sample. And other instances where you have to dig it up each time. If you have to dig up a sampling port each time, you introduce a possibility of getting dirt and anything else while you're digging away into the sample itself. So it really begins right at the sampling port design phase and making it accessible. And if you don't have that, if you're now saddled with doing a system that doesn't have a good sampling port, you really need to think about how you would make that sampling port better or even functional before you start using those data to modify how you're going to treat that system. So most sampling ports are really designed to get you should be designed to get you the best, cleanest sample. Because if it introduces any of the materials that would settle or are not atypical of what's really going out to the leach field, then you're going to make some bad decisions on your treatment process. So it should be a clean sampling port, and in some instances you may have to go out when you're doing your inspection and make sure that sampling port is clean for the next sample, either flushing it out or cleaning it or making sure it's accessible for the next time you come. Because that's so essential to being able to operate your system, is to have the good data.
And so, a clean or a dirty sample has maybe some dirt in it that's going to affect your results?
Well, it may have dirt, it might have the sludge that settles out and is not representative of what's going out to the system. Because in any system, if you slow the flow down, like in a distribution box, before it goes out to the leach field, then there's going to be some material that settles over time. And what's in the bottom of that D-box isn't going out to the system each time. It's settled. But if you disturb it, now you're getting the results of settling over months of time. And you may get a high BOD or suspended solids, think your unit is not working properly because it's throwing BOD or TKN or combined nitrogen, and you'll make a different decision on how you adjust that treatment system, and that's not going to be a good thing because you'll be chasing your tail.
So let's get into samples. What are we looking for in a sample?
Well, the sampling tells you everything. It really does. Is your unit operating properly? And even a cursory look at a sample, a visual look, can tell you what's happening in the unit. So if you see, for instance, you pull up the sample and it's very cloudy, and the process is really one that's supposed to clarify, right away something's happening. Either there's extra biological growth, or maybe you dip too down into the D-box when you shouldn't have, or you didn't get a clean sample. But provided that you get a clean sample, the sample parameters tell you everything. For instance, if you're in a denitrification unit, where many of us, that's what is chief on Cape Cod, denitrification units, and you take the sample and it shows up that there's huge amounts of dissolved oxygen that you could measure right there on site, then maybe I'm not going to get the denitrification that I needed, because lower DO at the discharge would tell you that, that you have the anoxic conditions in the final stage of that would have led to better denitrification. If when you get back from the laboratory, for instance, you get a BOD of 0, well, that would be great for a secondary treatment unit. but it might indicate for denitrification that you're running out of carbon. So you look at that dissolved oxygen, you look at the BOD, and you'd say, wow, maybe I need to adjust the air here because I'm getting too much. It's chewing up all the BOD, or the biochemical oxygen demand, in the first portion of the system, not getting enough for denitrification, as indicated also by the oxygen reading I took right there. So it's key to understand, first of all, your processes that your treatment unit is supposed to do, and understand what different parameters should look at different stages of that treatment unit, and to say, am I there? Am I where I should be in order to have situation conducive to remove what I'm trying to remove? And then with nitrogen, it's a pretty simple thing. You have ammonia coming out of an oxygen unit. It gets nitrified, and that you need a lot of air for. So you might take an intermediate measurement in that aeration chamber. If that aeration chamber has got no oxygen in it, you might have a problem. As you go through that nitrification, now you have to denitrify, which means you have to shut the air down a bit, and in fact, quite a bit. So if your second chamber where you're doing the denitrification, you're picking up oxygen, a lot of oxygen, you might not be able to denitrify. So all of these things should inform how you would make adjustments to your system. And I should say that some units, some denitrification units, are pretty binary. They're either off or they're on, so you can't make a whole lot of adjustment. But it might explain to you why you're getting poorer results. And so I think if I had one message to throw out there, understand the processes for the contamination removal that you're trying to achieve. Look at where the different steps in that occur in the system. And we just explained like the denitrification process. And then take some field measurements or even some laboratory measurements in certain aspects of it, so you know that it's going along and progressing the way it should in the field. This could explain lack of performance and help you make the adjustments, if indeed they're even possible in the particular treatment unit that you have.
So samples will tell you quite a bit about how your system is performing.
Yeah, well, samples is really the whole picture. I mean, there are some visual cues. If you go there and the thing's turned off and there's nothing working, then you've probably got a pretty good clue that the system isn't going to remove what it's supposed to remove. But given all the visual cues, nobody's unplugged it, you see everything working, you look down there and you see the bubbling, and everything seems to be like the unit looks like on a showroom floor, then you'll say, okay, now I really need to look at the chemistry of what's happening and the biology of what's happening in the system. And we did produce a while ago a little booklet that will be available, and we'll make it available. And it's sort of a key or a dichotomous key to go down to say, if this is happening, what should I be looking for? And that really walks you through also the nitrification, denitrification process. But again, they're all different technologies. We're just primarily focused on the nitrogen right now.
And while we're talking about nitrogen, can we briefly go over the different forms of nitrogen that you might sample for?
Sure. What's usually required for nitrogen is they want to know what's the total nitrogen out. So usually that's TKN, or total Kjeldahl nitrogen, which includes ammonia and all your organic nitrogen, plus your oxidized forms, which are nitrite and nitrate. So you've got TKN plus nitrate plus nitrite. That equals total nitrogen. And that will indeed tell you your total nitrogen picture. But if you break that down a little further and look at each of the components, you might get a hint at how, for instance, your unit is really operating. One example would be ammonia. If you see a high total nitrogen and you look and it's TKN, you might want to know, well, is that mainly ammonia? which means my nitrification isn't working? Or is it all organic ammonia, which means somebody's dumping bags of dog food down there and it's just going right through the system? So there are hints you can get by looking more carefully at the species of nitrogen or the sections of nitrogen that are part of the total nitrogen picture. Another key one, for instance, is nitrite. Nitrite you don't hear much of because it's very transient, but if you have a high nitrite, that means the nitrification process may not be going to completion. It's only going to nitrite, and it's not getting to nitrate, which is usually the most common pathway before denitrification. Then you might suspect that there's some toxic element getting into the system that's stopping that second part of the process. And that's very diagnostic, for instance, at schools. When a system isn't working, they might see high nitrite because there's some quaternary ammonia being used to clean floors, and that's toxic. So it would stop the process midway. But unfortunately, nitrite may be visible when a system first starts up also. If you should see that like within the first couple months of a system startup, you might see high nitrate, but then that will disappear because the second part of the nitrification starts. But before we go too much further, I want to say everything that denitrifies or goes through the nitrogen cycle is not completely understood. There are some times in which everything might look like, oh boy, I'm really in trouble here, but you really denitrify. And there's some mysterious things in the universe, and it's not only more complicated than we can imagine, and we can't imagine how complicated it can get.
So what about some of the other sample parameters?
Well, the big ones are Bod and suspended solids. And we talked a little bit about Bod, and BODs, particularly in denitrification. If you're running out of BOD, that's the food for denitrifiers. That's what they actually use. It's organic food, the carbonaceous food. And if you have a 0 BOD or below detection limit at the output of the system, you can bet that you're probably limiting your denitrification because it's running out of food. So if you see poor denitrification and you see 0 BOD at the end, then you've got a carbon problem at the end of the system. And there's not much you can do about that other than there are artificial forms of BOD that you can add. In fact, some of the treatment units actually have slow feeds of a BOD compound to feed at the end based on the flow in. These get a little tricky because if you have a system like that, you really have to watch how that's metered in at the end, or your BOD might be so high that your leach field will be impacted. Another real key one, and we see this on Cape Cod a lot, is alkalinity. It's not part of the regulatory measurements many times, but it's key in understanding whether you're getting nitrification. That is the conversion of the ammonia to nitrate, which is precursor to denitrification. If you don't nitrify, you pretty much can't denitrify. So you need to have, for that stage, something called alkalinity. And alkalinity is really a carbonate, which is an inorganic carbon, something we couldn't use, for instance, for food. But those bacteria that make that conversion from ammonia to nitrate, these are something called chemolithotrophs, which means they use inorganic carbon and they need that carbonate. We typically don't have it in our wastewater at high degrees here because we don't have limestone deposits where we're getting our water from. Our water is typically pretty low pH and no alkalinity. Our wastewater, it gets added to by our soaps and the food that we digest and throw out into the system. So it is very typical that the alkalinity becomes limiting. And that we can do something about. We can put baking soda down there, which is sodium bicarbonate, which is people could use that really in their laundry water and it wouldn't hurt and it would be a good thing. It sort of enhances sometimes the action of detergents. They could just dump the baking soda in every once in a while, flush it down the toilet. It doesn't hurt. It's generally used in refrigerators to get rid of odors and things like that. So when you're done with using it in that for your fishy refrigerator, you can throw it down into the toilet bowl and flush it away. Don't do it as a big brick, though. I mean, we get enough big bricks going down there to begin with. So just flush that down in like a powdered form, and that would be fine. Doesn't hurt the pipes. So alkalinity is really key, and we have alkalinities around here in our wastewater somewhere around 150 to 160. What we really need to nitrify much of the wastewater should be up around 200 to 300. For instance, in Florida or other parts of the country, typical wastewaters run in the 400s, and that's plenty to nitrify all of the ammonia. But the more concentrated our wastewater is for nitrogen, which it's getting more concentrated here, you really have to take your influent nitrogen, which is somewhere around 60, multiply that by 7, and that's probably the alkalinity necessary to totally nitrify. Now, in denitrification, you get some of that back, so you don't need that total 7 times 60 or 420 alkalinity, but you do need something more than what we typically give it. And many times we find that is the problem with some of the systems that aren't denitrifying because they can't nitrify. You'd get a key to that in your discharge because you'd see a lot of ammonia. If your total nitrogen comes out in your TKN, which includes ammonia, remember, if you're coming out at, say, a 30 total nitrogen and 15 or 16 of that is ammonia, then you know you're not nitrifying completely. Sometimes I've seen them as high as all of it coming through as ammonia. In fact, if you ever want to know if somebody shuts a unit off, then your discharge will be primarily ammonia. Because if there's no air coming out of a septic tank, about 80% of that TKN will be ammonia.
So a quick solution, and probably one that's not terribly harmful to diagnose that, would be to have the operator inform the homeowner to just try adding some baking powder or baking soda? Baking soda.
Okay. And they could do that, themselves. The operator could do themselves. There are some units where it is bled in with a little meter. Put it in. Mostly those are commercial units, and it's generally not necessary if a homeowner takes it to heart and just flushes a little bit down. And it's probably something you want to try first for a period of time and then go back within a month and take samples to see whether that is the real cause of your nitrification issue. Because there are other issues that could happen, and we don't know what, for instance, medications do. Certain medications, you would expect antibiotics would affect the system because they kill bacteria. But there are other things that affect the metabolism of bacteria that we don't know about. Certain, drugs that people take normally, and of course illicit drugs, we don't know anything about how those affect things. So these are all sort of, there's a big picture, a puzzle when a system doesn't work. The big pieces, the easy ones to put together or discount, would be alkalinity, oxygen, pH. Those give you the biggest hints. But then you really have to get down into the weeds. If all those things you've checked and everything looks normal, now's the time to really start some further investigations.
So there are lab samples, but then there are also field measurements.
Yes. Both of them inform how the system will work. Field measurements, of course, are, as the name implies, done in the field, sometimes with an instrument, sometimes with some sort of field test kits. The key thing to remember there is that, again, you need good information. So if you have a field instrument, it needs to be calibrated, needs to be kept clean, needs to be ready to be used, because many times you'll see somebody with a dissolved oxygen meter that's not been calibrated in months, or a pH meter that has not been calibrated against standards in months. And, it's just like any computer program, garbage in, garbage out. Garbage in, that information you receive, if it's garbage, you're going to walk on it, and it's not going to hold it up. It's not going to work. So if you have field instrumentation, guard it carefully, calibrate it, keep it clean, because particularly pH and dissolved oxygen, which are key parameters that you can get an idea of how a system works by intermediate measurements within the system, it's essential to keep that just pristine and ready to go and calibrated. With your field test kits, they run the whole gambit from good test kits to bad test kits. You should know the limitations of the test kits you have. And if my good friend Jose Amador did a study on this with some of his graduate students and found that a lot of the test kits work much better if you're inside. If you actually took the sample and walked inside and ran the instrument, because a lot of them are visual. So depending on the weather, the lighting, everything, if you can make that consistent, you'll get a better number and you'll be able to, again, walk on good information rather than go on bad information. Nothing worse than making an adjustment on a system that on bad information, and then it just goes from bad to worse performance. It's just discouraging. For field sampling, it's essential that you treat the sample proper. If you take a sample, certainly most of them have to be on ice. Some of them need to be preserved. So your TKN ammonia samples have to be preserved. So they should be in preserved bottles. And you can't sort of keep those bottles in the hot sun in your back seat while you're waiting to take the sample. You should sort of make sure, because each one will have a drop of sulfuric acid in it, or if you're doing other things, might have hydrochloric acid in it. And you want to make sure that those are fresh bottles from the laboratory. Treating them after you take them to keep them on ice. A lot of these parameters change with biology. Everybody thinks, well, okay, how can nitrate change at all? Well, a nitrate sample is not preserved. So if you take the sample and add some ammonia in it, that could convert, theoretically, in warm temperatures if it had the nitrifiers in it. So you want to make sure that one goes on ice. The preserved sample should be on ice, although the acidity will keep any bacterial action from happening. BODs, absolutely, you want to keep those on ice. Suspended solids the same way. So treat the samples. There's, standard methods will tell you exactly how they need to be preserved or kept on their way to the laboratory. And the other key thing is get it to the laboratory as quickly as possible. If you're collecting anything for bacteria, that is really essential that you watch the temperature of it and that you get it to the lab. A lot of those holding times are 6 to 12 hours. So, you're collecting in the morning and you're doing a bunch of samples. You really have to watch. You can't leave them in the back seat, especially a day when in the summer where you're, that'll crank that heat right up. So just remember that these should inform you on how you work. And it's like anything else. If you got a busted speedometer, you don't know how fast you're going, and you'll probably get a ticket. But if that speedometer is right on, you know exactly the limitations of what you should be doing, and you'll be within the specifications, and everything will be fine. It's the same with anything else. Good information is what drives good decisions, which in turn should drive good data coming out.
So laboratory samples, you need to pay attention to the bottle type, the preservative, and ice, whereas field, you're taking them right there in the field, so just making sure you're in the proper location and free-flowing. Yeah,
free-flowing, and also it's the calibration of your instruments, which is big. I mean, it's very essential, particularly pH and For instance, here at the test center, we calibrate our pH meter daily with 3 standards. Dissolved oxygen daily. So, keep your standards up to snuff too. And realizing that it's not cheap, it's not inexpensive to do that, but it's also necessary because it'll cost you more in the long run to make a bad decision based on inaccurate data.
So let's say you as an operator or even a Board of Health agent has looked at all of the things we covered so far as samples being taken properly, calibration, etc., but you still can't figure out what is amiss. What are some last things you can talk about that you could look into?
Well, it's always tricky. When you're an operator, you're in somebody's backyard, and if you have a very good relationship with the owner, then you can be doing some of these things all the way along and giving them a hint that you're there a little bit extra because things aren't working right. But at some point, you're going to have to really find out what's going on in the home. And this gets tricky, particularly if you're looking at things like medications that might be affecting things, because people are usually a little shy about telling you those things, particularly if it's an illicit drug operation. You're probably not going to get that information. But there are other things like the true occupancy. If there are water meter readings, that you can get an idea of the true flow through the system. Is there anything happening in the household that you might want to know about? If somebody is, for instance, very ill, they're cleaning a lot more. And what kind of cleaners are they using? What kind of detergents are they using? Water use tells you a lot. Chemicals being used in the house tell you a lot. And of course, if there's any drugs that are being used, in the house, legal or illegal, that would tell you a lot. Some of those, as we have said, we don't know the impact on some of the systems. But the other things are I just discovered this recently, for instance, some heaters, some of the real sort of new heaters that are highly efficient, have a condensate which is sent to the septic system. And some of that is pretty acidic. It's buffered by marble chips or something in a little container past the condensate. But if that's not maintained and you're putting a lot of water out, particularly running an air conditioner or a heater a little bit more, which some folks do, they run their heat, they keep their house really warm. So those things can affect it, and you just should know about them. Some of the more obvious ones are some pumps that end up getting connected to a septic system that no one knew about or no one thought about before, sumps. Some other discharges that are going to a septic system, like backflush from filters, things like that. So you really, at that point, you have to get down to the nitty-gritty. And realizing that this is often a pretty sort of tenuous steps you need to take with a homeowner, because some homeowners say, yeah, I really want to get to the bottom of this, and the others, they just want to point a finger and say, hey, look, the thing doesn't work, I want to get rid of it. So this is nothing there's no textbook for this one. You have to sort of feel your way along. If you've done everything you can mechanically to do it, you've made your measurements, some of them you can't explain. Now it's time to really start looking at things. And it could come from anywhere. And I'm sure that I have not seen the whole panorama of things that could happen in a septic system. If there's some little kid in the house that just feels like he needs to dump something down the toilet, when you're a little kid, sometimes watching that stuff go away, that's fun, and if it's colored, it's even more fun, and who knows what happens inside of a house. But if you make the homeowner aware that there's something going on, and you can give them some even mild interpretation of what it would take to make those results you're seeing, maybe they can help you put the puzzle together, because oftentimes it's a puzzle. And then there's other things that, for instance, not knowing the true influent value of your system, because a lot of these systems you can't get at that. So if your true influent is, for instance, in a nitrogen in the hundreds or 150, and you're getting poor results out, not meeting 19, that would be totally understandable. So there will be instances where you just got to throw your hands up and say, I can't figure it out. Look at that influent. Try to get a good influent number. Even if you can't get a good influent number, if you go to the influence side of that system and you measure the total nitrogen and it's up over 100, even if it's remixed, you know that there's more than the typical coming into it. So that gets a little bit into those extreme circumstances. And the more you understand about how your system should work, how it is working, because you've taken all the field measurements and you've got a lot of data from a laboratory, the more you'll be able to say, well, this is the case. And in some instances, you might have to make that appeal to the Board of Health that you understand that these influent numbers are extremely high, or this is happening in the house, to explain those circumstances. Because as we do this more and more, particularly to address TMDLs or maximum daily loads here on the Cape, there's going to be a higher level of accountability. And with the higher level of accountability, there's going to be more questions to the operators, more questions to the homeowners, what's happening. And collectively, we can put together the picture of why a system doesn't work, or maybe it is working how it's designed, but getting extremely high influent. Then the more we can put that picture together, the more we'll understand what we really have in our toolbox to remove nitrogen or any other contaminant in the Cape. Or wherever you're investigating it, just to get a better idea how these systems are really working.
Just a couple quick examples of what might be going on in a system. Let's say you have high TKN, high total nitrogen, but your nitrate and your nitrite are low, and you have high BOD. What's something that might be going on?
Well, you have to first look if you've got high ammonia or high TKN, is it organic or not? But let's assume that most of it's organic, inorganic ammonia, and you're getting low nitrate. I think the first thing I would look at is I'm not nitrifying. I either don't have enough air, so I'm always going to look right for the aeration and say, is it adequate? Does it look like the pump's running? Is it possible somebody shut the pump off and just turn it on before I got there? Because that's happened. The other thing I'd look at, the two key, there are oxygen and alkalinity. So you look at oxygen, alkalinity, and even with the alkalinity, I might take a quick pH reading. If you didn't have an alkalinity measurement on site, if you didn't have that little kit or you didn't have any field lab information, you'd say, gee, why don't I test the pH? Most systems operate optimally at a pH of 7. So anywhere between 6.7 and 7.5, above that, you'd start thinking, what else is happening here? If you're in that range, you're probably okay for pH, but you still might not be okay for alkalinity.
So this has all been very informative, and I think this is great. What are the key points that you want folks to take away from this?
I think the takeaway points are, first of all, make sure in your design, get to the designer before they put it in to give you good sampling ports. If you don't have good sampling ports, make good sampling ports. Somehow make them accessible so they're not crudted up each time. And, of course, secure so nobody can dip their hands in when you're not there. Second thing would be understand your process. Understand how it works, where certain measurements could be made to give you diagnostics on the system when it does not work. The third one would be get good samples. And sometimes that means taking samples that aren't quite regulatory samples. And it's hard because that costs money and it's going to cost somebody money. But if you get a good feel kit for some of these parameters and actually go that extra mile, measure that alkalinity, find out whether that TKN is ammonia or whether it's organic or not. Those things are all diagnostic. Dissolved oxygen meters, everything you have, keep it in good shape, because the biggest thing to remember is good data in means good decisions can be made. The final thing is, when all else fails, or intermediate, if you have good relationship with the homeowner, is try to understand what the use pattern is, because that's what's going to drive those performance things. And if you can do that, if you can have a good relationship with the homeowner to the point where you both mutually just want this thing to work, then you're bound to have success. Now, I understand that a lot of homeowners, this is a total inconvenience for them. So you're going to have to navigate those channels carefully, but guess what? They have to be navigated. The homeowner most likely got an IA system because they wanted something different. They either wanted that extra bedroom, they wanted the extra use of the property. So subtly, you're going to have to make them understand that this is a regulatory thing. As we get into this more on Cape Cod, we're going to have higher levels of accountability and higher sort of expectations for performance that are going to have to be met. So in that instance, you're going to have to provide that homeowner, coax them along. And I know, you're not their therapist, but you will have to understand that you are going to have to sort of embed in them sort of a responsibility for the performance of that system. That's going to be some contention in some areas, but hopefully that will be rare. You'll have mutual sort of goals here to both make it both inexpensive, sustainable, and whatever to make that unit work. But that's really the crux of it, because alternative septic systems are a good piece of our infrastructure that avoids having to run expensive sewers or having, disruption for sewer lines. But it is wastewater, and we do need to deal with it responsibly. So the more you can sort of encourage a homeowner to understand that process, much like they understand the fact that they need a heater that works in the winter, then I think we'll go a long way for making this a sustainable and realistic part of our infrastructure into the future. That's a very useful and really something that is good for the areas, particularly the areas that are impacted.
And you, if folks have questions, you can answer calls?
Oh, certainly. I mean, my email information is there, and I very rarely will just avoid an email unless the same question comes in 50 times. But, and also we have the information in the packets, and we'll make that available on our website, because there are simple diagnostic tools. And I know, I want to say that there are a lot better operators out there than I would ever pretend to be. So if you have any ideas or any examples of things or any problems that you saw were pretty unique and that you solved them in a good way, send them in and we'll put them up on the website. It'll be anonymous unless you don't want it to be, but we'll probably make it anonymous anyhow, because your experience can really benefit some of the folks out there who are really having a hard time with this. A lot of big treatment plant operators came into the field thinking, this is a piece of cake. I operated a 0.8 million gallon plant. I should be able to do this. A lot of different subtle nuances that need to be addressed. And there's a lot of the folks in the trenches, a lot of people listening to this that said, I think somebody could benefit from this or that, and I'll throw that out there, because we'll make it out there. We'll put it out there for you. So thanks for listening, and for those folks who are listening to it, hey, good luck out there. Stay safe, wear gloves, wear protective gear. I have to say all those things.
Excellent. Well, thanks so much, George, and we'll make our resources available on our websites where you can find that information here. Thank you.